and welcome to this module on telomere restriction fragment, or TRF for short. So telomere restriction fragment is a method of quantifying telomeric lengths in DNA samples of eukaryotic cells. So let me go ahead and begin with the idea of telomere restriction fragment by starting with an overview of the various steps involved. The first step in TRF is DNA extraction, where you have a sample of cells and you extract the DNA from those cells. You'll then evaluate the DNA's integrity. This is an important step, and I will discuss why that is in a bit. And after you evaluate the DNA integrity and ensure that your genomic DNA is indeed intact, you will perform genomic DNA digestion, leaving the telomeric repeats undigested. And I'll discuss how genomic DNA digestion is made possible in the next slides. Now, after you digest the genomic DNA and are left with subtelomeric regions and the telomeric repeats, you will perform southern blotting. Importantly to this step is the construction of an appropriate DNA molecular weight ladder that depends on the approximated telomeric repeat lengths, or the telomeric lengths in the organism that you're studying. You'll perform agarose gel electrophoresis as you do with typical southern blotting. And when it comes to the hybridization step and the detection of your southern blot samples, you'll hybridize the telomeres with probes that are complementary to the telomeric repeats. And lastly, you will perform some mathematical analysis to figure out the average telomeric lengths in your sample. So let me begin with the first step of TRF, which is DNA extraction. So for DNA extraction, you can utilize phenylchloroform extraction. I have a whole module on phenylchloroform extraction, so I will not go over this right now. But in addition, commercial DNA extraction kits can be used, obviously, for the DNA extraction part. The second step is to evaluate the DNA integrity, and this is quite important because you want to make sure that your genomic DNA is indeed intact. If your genomic DNA is not intact, then that will influence subsequent steps and the mathematical analysis of your telomeric lengths. So to evaluate the DNA integrity, you can perform agarose gel electrophoresis and look for signs for intact DNA and signs for degraded DNA. Now, intact DNA will appear on an agarose gel as single compact crown bands. So, for example, you can take a look here at lanes 1, 3, and 5. In lane 1, 3, and 5, you can take a look at lane 1, for example. You have a crown-shaped band. In addition, you have only a single band and you do not have any smears or any shifts. So the fact that you have single compact crown-shaped bands, such as what you see in lane 1, 3, and 5, all indicate that you have a intact genomic DNA within the samples of these respective lanes. On the other hand, if you see smears or forward shifts in your bands, then that indicates that your DNA has some degraded elements, and this cannot be used for TRF. This is important to recognize, and that's what makes the evaluation of DNA integrity an important step in TRF. Again, if you have degraded DNA, then that will affect the subsequent analysis of your telomeric lengths. So very briefly, if you take a look at lane number 2 and lane number 4, you'll see signs of degraded DNA. For example, in lane number 2, you can see that there is a forward shift in the band. On the other hand, in lane number 4, you can see a large smear here that indicates the presence of degraded DNA. Now, after you perform your evaluation of the integrity of your DNA sample, you'll perform genomic DNA digestion. And to do so, you'll utilize restriction endonucleases. Importantly, the reason you can do this with restriction endonucleases and not digest your telomeric repeats is because there is a relative lack of restriction sites in the subtelomeric regions that permits the digestion of genomic DNA but not the telomeric repeats. So the outcome is that your genomic DNA will be digested into small fragments while your telomeric repeats and the subtelomeric regions are undigested. Of course, when you are performing the analysis part of your TRF, you'll account for these subtelomeric regions, which are constant in length, relatively speaking. An important step in TRF is the construction of your DNA molecular weight ladder. The range of the ladder is dependent on the organism of question. In addition, in organisms with long lifespans, example, humans, the age of your subject is also considered. So, for example, if your subject is a 20-year-old human, then the range for the ladder will be different than if your subject was an 80-year-old human. In an 80-year-old, we would expect shorter telomere lengths, and thus you will use a range for the ladder that accounts for that. And for this step, it is commercial DNA ladders that are often used. So the next step is to truly start your southern blotting and perform the agarose gel electrophoresis of your sample, whereby you have extracted the DNA, evaluated its integrity, and digested the genomic DNA, leaving only the telomeric repeats and the subtelomeric regions as undigested. Importantly here, the percentage of agarose gel that you use should depend on the expected average length of telomeres of the studied organism. If it is human telomeres that you're studying or telomeres of organisms with long lifespans, the age of the subject should also be considered. For example, if you have a subject with lower age, then you will utilize a lower agarose gel percentage than if you have a subject that is of higher age, whereby you'll utilize a higher agarose gel percentage to permit the appropriate movement of the telomeres with their respective differences in lengths in the agarose gel. In the hybridization step within your southern blotting in TRF, you will utilize a labeled sequence of oligonucleotide repeats that will be complementary to the telomeric repeat. Now, the labeled sequence of oligonucleotide repeat can be consisting of 3 repeats that are complementary to the telomeric repeat. And as for the labeling of this oligonucleotide, it can be labeled at the 3' end, for example, with digoxygenin or DIG. On the other hand, it can also be labeled with a radioactive isotope. And once you've concluded your southern blotting, the next step is the analysis part of your TRF. You will scan your southern blot and you will perform a image processing step via particular software to graph the optical density versus the DNA migration distance. Once you have that information or that data of the optical density versus the DNA migration distance, you will utilize that data to obtain the optical density that has been adjusted for the background. I'll talk about how that is done in a bit, divided by the molecular weight versus the molecular weight. Obviously, this right here would be in the y-axis and the molecular weight here would be in the x-axis. Now, to obtain this equation, or I should say to obtain this graph from the previous graph that you obtained via an image processing software that you've utilized on your southern blot outcome, you'll utilize the following equation that I'm underlining. The y here is the migration distance, and on the other hand, the x that you see here is the molecular weight in the new graph that you are creating. Importantly, you should understand that A0 to the left and A1 here are constants. And once you've done the following conversion that I just outlined, you can utilize the following equation to obtain the mean telomeric length of your sample. Importantly, you can see here that we have the summation of optical density values at I and the summation of optical density values at I divided the molecular weight at I. And importantly, I here just refers to a particular position. So you are here getting a summation of the optical density at a particular position, and we'll call it I for the sake of mathematical simplicity, divided by the summation of the optical density at that same position divided by the molecular weight at that same position. And obviously, you're summing up all the different optical densities and molecular weight statistics, or data, I should say, that you are obtaining. At the end, you can notice here that what we end up with is an optical density value, or an optical density unit, divided by optical density over molecular weight, which is equal to optical density multiplied by molecular weight over optical density. And thus the optical densities cancel out and you end up with molecular weight only. The molecular weight which you obtain is proportional to the mean telomeric length of your sample. And this concludes this module on TRF.